Hello everyone, welcome to topic 3.1, Intermolecular Forces. For this, by the end of the lesson, you should be able to explain the relationship between chemical structures of molecules and the relative strength of their intermolecular forces when two molecules are, or not just two, but molecules of the same species and then molecules of two different chemical species. So what are the intermolecular forces and interactions there? We have more essential knowledge that is linked to describing that, but there are no equations. So beginning with notes, intermolecular forces, or IMF, are the attractions between atoms, ions, or molecules. And these hold them together. There are 6 different types of intermolecular forces. They differ in arrangement of the electrons. Intermolecular forces can explain why carbon dioxide is a gas, water is a liquid, and silicon dioxide is a solid, even though they are all made from only 3 atoms. To determine which type of intermolecular force a substance will exhibit, you need to look at the types of atoms that are present in the sample. Start by identifying the types of atoms in the sample as either a metal or non-metal. And so we have this table to help us do this. Okay, so we have our weakest intermolecular forces, which are London dispersion forces. And then we have dipole-dipole. We have our traditional dipole-dipole, which is summarized in the left column. And then we have hydrogen bonding, which is a super dipole-dipole, super strong. Okay, so when we say dipole-dipole, we usually refer to this one, and then hydrogen bonding is separate. All of these together are called van der Waals forces. Okay, so these are ones that are specifically between molecules or atoms, not ions, not metals, not network covalent compounds, although everything we see for London dispersion forces, everything has London dispersion force, but specifically these are between, all of these here typically are talking about substances that have a discrete unit that exists on its own. Okay, but everything in general has a London dispersion force. The dipole-dipole exists between molecular covalent compounds, so we'll write that in. Okay, we also have ionic, metallic, and network covalent, or covalent network. Okay, and then we have descriptions for all of these. So London dispersion is for all polar asymmetrical molecules. For dipoles, if it's hydrogen bonding, it has to have a hydrogen bonded to nitrogen, oxygen, or fluorine. Ionic, that is an ionic bond, that's what we're talking about, is metals with nonmetals. Metallic is metal only, and then covalent network is very specific to these substances. There might be some more, but those are the specific ones. So if we look at nonmetals only, we have London dispersion forces. London dispersion forces occur in all substances, so they should always be considered. They are the only type of intermolecular force present in nonpolar molecules. Okay, when we say nonpolar, everything has intermolecular forces of some persuasion. They can be very weak or they can be very strong. If it is a nonpolar molecule, the only one present is the London dispersion force. These forces are caused by the motion of electrons within an atom or a molecule. As electrons move around within the atom, there is a chance that they are unequally distributed. When this happens, it causes the atom or molecule to have a temporary dipole, due to there being an excess of negative charge, or partial negative in that area, in one place. And then that means that in an area that is deficient of electrons, so if you have it all collect to one side, there's going to be an area deficient in electrons and therefore will be more positive. The temporary dipole in one atom or molecule causes the neighboring atoms or molecules to change. Okay, so they end up, if we scroll down, we see it here. This one might have an induced dipole, and because it has an induced dipole, it's going to tell its neighbor, hey, bring all your negative stuff to meet my positive. Okay, so they will cause dipoles to happen in each other. Okay, dipoles can also happen because they hit each other and then push the electrons to one side over here, and then this positive region here's brought these electrons closer to it by attracting. So an induced dipole. The temporary dipole in one atom causes the neighboring atoms to change. The negative end of the temporary dipole repels electrons while the positive end of the dipole attracts, that we see in this diagram. When the neighboring species of electrons move, this forms an induced dipole. So when this one makes an initial temporary dipole, it induces a dipole in the other. This means that it is electrostatically attracted to the first atom or molecule. This is usually very short-lived occurrence and will return to being evenly distributed. This is why London dispersion forces are considered weak. So the ability of an atom to form a temporary or induced dipole, so that ability to form the temporary or induced dipole is known as polarizability. How easily can it polarize itself, or can it be polarized, right? Creating a positive end and a negative end, two poles on that particle. London dispersion forces are stronger in an atom or molecule that has more electrons. This is shown in the halogens. Moving down the periodic table, fluorine to iodine, they change in state from being gases to liquid to solid. The increase in London dispersion force is due to the increase in electrons in each of those atoms. So fluorine has very few electrons, but iodine has a lot. That means that iodine, by having more electrons, is more polarizable, meaning it has more electrons that it can push around. And so it can create a temporary dipole that is one stronger and more easily formed because it has so many electrons. Large molecules will have stronger London dispersion forces because of the increase in electrons, and that increases their polarizability. Another factor that increases the strength of London dispersion forces is the shape of the molecule. Long, thin molecules have more surface area and are more polarizable, while short, round molecules tend to have less surface area and are less polarizable. The more polarizable the molecule, the stronger the London dispersion force will be, and that's in general. This is also enhanced by pi bonding, the presence of double or triple bonds, because you concentrate electrons in one specific area, so it's more likely to have the ability to be polarized there. So there's three things that cause or impact polarizability, right? So three things. The first is the number of electrons. The second is its shape. And the third is the presence of pi bonding. And these all contribute to the London dispersion force strength. Okay. Now, dipole-dipole, this is how polar molecules interact with each other. Okay. Dipole-dipole interactions occur between molecules that have a permanent dipole due to them being polar molecules. Molecules are polar when their electron distribution is asymmetrical. It is always a good idea to sketch the molecule to determine if it is symmetrical or not. Dipole-dipole interactions are similar to London dispersion forces, except that the dipoles are permanent, so the attractions are generally greater. Generally. There are exceptions, and that is usually a tested thing, but they give you an exception and ask you to explain. The partially positive end of one molecule is attracted to the partially negative end of a different molecule, and so on throughout the system. And you can see that in this diagram below. Dipoles can be measured by the dipole moment of the molecule. Dipole-dipole interactions are stronger when the substance involved is more polar, meaning that their electrons are more unequally distributed. Be sure to consider the electronegativity values of the elements involved when you are looking at these. If the dipole-dipole, or if the dipole in the molecule is super strong, we end up with hydrogen bonding, and this is very specific. Hydrogen bonding is a confusing name for this type of intermolecular force because it is not a bond. It is an attraction, just misnamed, but we're sticking with it. It occurs in molecules that contain hydrogen to nitrogen, hydrogen to oxygen, or hydrogen to fluorine bonds. Nothing else. The hydrogen bond interaction is when those are interacting. OH to OH, NH to OH, any of those that it has to have both of them interacting for it to be considered a hydrogen bond. If it's OH group to maybe this HCl up here, that is a dipole-dipole interaction. Okay? For it to be a hydrogen bond interaction, it has both interacting parts have to have the hydrogen bond components. They don't have to match, but they have to have one of these three interacting with each other. Okay, continuing. The attraction isn't the bond itself, rather the relatively large difference in electronegativity between NO or F and the rest of the molecule causes it to have a large dipole. This dipole causes a strong attraction to the dipole on the molecules surrounding it. The hydrogen bonding intermolecular force is strongest, and in this order because of the differences in electronegativity, and it is stronger when you have multiple sites for hydrogen bonding. So we have to have these bonds present, and if we have more of them present in the molecule, the hydrogen bonding is even stronger. So here is a list of naming some of the interactions for you guys to review. Use this when working on activities and stuff. I'm not going to read through all of it, but it does give you what types of substances we're talking about, and then the type of interaction, how we would call it. Okay? So, in large biomolecules, so like proteins and stuff like that, macromolecules, in these molecules, the covalent bonds and intermolecular and intramolecular forces can determine their shapes. For example, in DNA, base pairs CG and AT link together via hydrogen bonds, shown by the dotted lines in the diagram to the right. This phenomenon occurs in many biological molecules. Proteins fold a lot of the time, a good chunk of the time, because of hydrogen bonding and intermolecular forces with stuff surrounding it, like hydrophobic and hydrophilic, water-loving and water-afraid interactions with the solutions it is in. These are not technically intermolecular forces, but we do consider them with intermolecular forces. So we have ionic, which is the attraction between metals and nonmetals. Remember that ionic bonds are stronger when charges are larger and ions are smaller, and this is explained by Coulomb's law. Metallic interactions or metallic bonding occurs between metal atoms and can be just for one type of metal, a pure substance, or different types of metals in a mixture called an alloy. These metallic attractions are due to multiple metallic cations being attracted to a delocalized sea of valence electrons. The intermolecular forces are stronger when we have smaller metallic cations and when we have more valence electrons. And finally, covalent network. These occur between carbon, silicon, and carbon, oxygen, or silicon, or some combination therein. These attractions are due to multiple covalent bonds forming a very large macromolecule, like diamonds. The intermolecular force is stronger when there are more covalent bonds formed. Okay, so they create very large covalently bonded lattices, and these end up being very strong forces. Okay, so these are important to consider because we will keep coming back to them. These are physical properties of, and lattice energy is a chemical property, but these are properties that result because of intermolecular forces. You will usually be asked to explain or describe why these happen, and that's actually in these homeworks. And you always want to consider how the attractive force is changing. Okay, so together we're going to do the I do's and the we do's, and then you can do the you do's on your own. Okay, so pentane and octane are both hydrocarbons. Okay, when we look at these, we could draw them out, but in general, these are not polar because the CH bond is not a polar bond, and so they have no polar bonds. They also, if you were to draw them out, you would see that they are very symmetrical. The type of intermolecular force present then is just London dispersion forces. Okay, and then now we want to predict the higher vapor pressure. So if we look up here, vapor pressure, if we increase the intermolecular force, we decrease vapor pressure. So we want the one, right, that would have lower intermolecular force because then it would have higher vapor pressure. Now we're going to explain why. So the lowest intermolecular force would be pentane because it has the fewest number of electrons. When we're talking about London dispersion force, remember we want to talk about the number of electrons, the size, and pi bonding. Well, if you drew these out, you would see that there is no pi bonding. It's not going to happen. So then we're going to talk about electrons and size. Well, the one with the more electrons and the bigger molecule will have greater London dispersion forces. That means that octane has really big London dispersion forces because it has more electrons and it is bigger than the London dispersion forces in pentane. So pentane we would expect to have a greater vapor pressure, right? So the London dispersion forces are weaker. Should use good grammar. So the attractive force is less and a gas. Right? Vapor pressure is just saying how much of what pressure of the liquid above it is actually a gas of the same compound. Right? They're like liquid water, you have a cup sitting of water and it eventually evaporates off. That's because a little bit of it at a time does go into the gas phase, and that's part of its vapor pressure. Okay. So because the London dispersion forces are weaker, the attractive force is less, so they don't stick to each other as much. So the molecule is more polarizable, is less polarizable and more likely to go into the gas phase. It'll go and become a gas more easily. You don't have to overcome those intermolecular forces to make it a gas. So the boiling point of HF is 293 hydrogen fluoride, whereas the boiling point of fluorine is 85. So 293 versus 85. Determine the types of intermolecular forces present. So we have HF and we have F2. Now everything has London dispersion force. What else is it capable of? Well, we know that the HF is a polar molecule, so we can say dipole. But because it is H bonded to F, this is also hydrogen bonding. Whereas fluorine is nonpolar, and it's a molecule, like a covalent molecule, so it only has London dispersion forces. Now, using this information, please pause the video and explain the difference in boiling points based off of intermolecular forces. Okay, so HF has a higher boiling point because its intermolecular forces, especially H bonding, are stronger collectively than fluorine's. And that's all you really have to say, is leave it to its intermolecular forces. that because it has so many more, they're more attracted to each other and thus requires more energy to overcome that attraction and boil it. So now, using your notes, and go ahead and work on the you-dos and check your work as you go. Thank you.